Welcome on this lecture in heat transfer on natural convection in external flow. The learning goals of this lecture are that you get knowledge of the correlations that are given in the reader for the prediction of heat transfer by natural convection, and that you start to understand where these formulas came from for different cases of natural convection. First, let's look back at the classification of convection according to the flow regime. We had the options of forced convection versus free convection, external flow versus internal flow, and in this lecture we are going to look at free convection for external flow. And an example here is the cool air that is rising over a solar collector, and the air is rising. The flow is initiated by the density differences. The hot air has a lower density and is pushed upwards by the cooler air. What are the important dimensionless numbers? First of all, the Nusselt number, that is in fact the dimensionless heat transfer coefficient. Alpha is the heat transfer coefficient, L the length scale, lambda the conductivity coefficient. The second number is the Prandtl number, which compares the momentum transport due to friction with the heat transport due to conduction. The third one is the Reynolds number, which gives the ratio of inertial forces to viscous forces. And the last one, and that is the most important one, for natural convection, that is the Grashof number, which describes the relationship between the buoyancy forces of a fluid and the acting viscous forces. And we can see, of course, that the buoyancy is involved, is that gravity is here, and we see here the coefficient beta, that is the thermal expansion coefficient of the gas or fluid. Then we have a length scale to the power 3 and the viscosity to the power 2, and this means that for gases the Grashof number is usually very large. So now let's look at the correlation functions for natural convection. These will generally be expressions of the dimensionless heat transfer coefficient, the Nusselt number, as a function of the Grashof number and the Prandtl number. What are the applicability criteria? That is, what different kind of natural convection correlations can we find? Well, they will depend on the geometry, they will depend on the flow regime, and they will depend on the thermal boundary conditions. And of course, for a horizontal flat plate or for a vertical flat plate, for turbulent flow, for laminar flow, we will find different functions. Nusselt is a function of Reynolds and Prandtl. When you are trying to predict heat transfer in a certain case for engineering application, then it is of course important that you use the right correlation for the case that you are considering. In the dimensionless numbers, material properties appear, for example, the density or the viscosity. These properties are evaluated at the temperature of the properties, and that is the average temperature, where the average of the wall and the temperature at infinity. And this average temperature is also called the film temperature. There's one exception, and that is the isobaric expansion coefficient beta. And for the calorically perfect gas, beta is 1 over T infinity. Let's look at the first example. That is a vertical heated plate with a laminar flow and an isothermal surface. The plate is indicated here in red. It has a higher temperature than the environment. Gravity is pointing downwards, and here you see indicated the boundary layer in the velocity. Zero velocity at the wall, zero velocity at infinity, and in between there is a maximum somewhere in the boundary layer. The velocity boundary layer is indicated here, delta U. Temperature of the wall at 0, and temperature at infinity, going down to temperature at infinity, and there's of course a certain thermal boundary layer. And the ratio of these two boundary layers depends on the Prandtl number. The x direction is the direction of the flow along the plate. The y direction is the direction normal to the plate. For this case, the correlation expressing the local heat transfer coefficient, Nusselt as a function of x, is 0.508 times a number that depends on the Prandtl number times the product of Grashof local times Prandtl to the power 1 over 4. This product of Grashof times Prandtl also has a different name. It is also called the Rayleigh number. Note this is the local value, so that is the value for the x along the plate, and it varies. The numbers here refer to the formula numbers in your reader. If we now integrate this expression over the length of the plate, then we obtain the average value of the Nusselt number, and this can be written as a constant times Grashof Prandtl based on L to the power 1 over 4, and that's again the same power. And this expression will only hold for Grashof numbers or Rayleigh numbers below a certain critical number, and that is of course because we're here looking at the laminar flow. The constant C depends on the Prandtl number, and here are a number of values given. C ranges from something like 0.2 to 0.7 for the entire range of Prandtl numbers. To the right here you see a graph where the drawn line indicates the expression here. Nusselt is C times Rayleigh to the power 1 over 4 and the dots indicate the values obtained by experiments. And of course there is good agreement because probably the line was derived from the experiments. And that is how these correlations are usually derived. The next case we can look at is the vertical heated plate with a laminar boundary layer, but now we have a different boundary condition. That is, we have a condition where the heat flow is constant. And for a constant heat flow, the expression for the Nusselt number locally is 0.6 times Grashof Prandtl, which is the Rayleigh number to the power 1 over 5, and we see that here the heat transfer coefficient is thus smaller. The expression is valid for 10 to the power 5, 10 to the power 11 Grashof number in between. And note that here we have the heat flux given as a boundary condition. And then we can, for simplicity, use a different Grashof number, Grashof star, as is indicated here. And this Grashof star is defined as the Grashof number times the Nusselt number. And this is then, when we write it out in detail, it's the density squared G beta, the heat flux that is given, times x to the power 4 divided by the thermal conductivity coefficient times viscosity to the power 2. Well, can we see this if this is the case? Well, of course we know Grashof is rho squared G beta times temperature difference times length scale to the power 3 divided by viscosity squared. The Nusselt number we can write as the heat flux divided by the temperature difference times x divided by lambda. And this here you recognize, of course, alpha. And if we now multiply this, then we see that the temperature difference cancels and that the x becomes times x to the power 3 becomes x to the power 4. And then we obtain the expression of the Grashof star that we have given here. Now, if we have a constant wall temperature, then we had, just before, we had Grashof times Prandtl to the power 1 over 4. So we see indeed here that we have a lower heat transfer. We just had two cases where we looked at the laminar flow, and now we can look at the vertical heated plate with turbulent boundary layer and an isothermal surface, and that is the result given here in the graph. Here you see the Nusselt number as a function of the Rayleigh number, and you see that below a certain value we have a laminar flow, above a certain value we have a turbulent flow, and in this turbulent regime here we can write the average Nusselt number as 0.13 times Grashof Prandtl to the power 1 over 3. That is equation HTC 19 in your reader, and it is valid for Grashof numbers, Grashof times Prandtl between 10 to the power 9 and 10 to the power 12. That is indeed indicated here, 10 to the power 9, 10 to the power 12. Now note we see here that the power is 1, 3. Remember that in the Grashof number we had the length scale to the power 3. So length scale to the power 3 to the power 1 over 3 means that we have an L on the right hand side. Nusselt is alpha times L over lambda, so there's also an L, and this L on the left and right side cancels, which then means that for a turbulent boundary layer flow, the heat transfer coefficient is independent of the height of the plate. Now suppose we want to look at more complex shapes. Suppose we want to look at a cylinder. I can imagine that if this cylinder, that we will have a boundary layer develop around the cylinder and that it will be circularly symmetric, and that if the cylinder is very large, if the diameter is very large, then this will behave essentially the same as a flat plate. So when the diameter is much larger than the thickness of the boundary layer, we can approximate the relation for the Nusselt number of the behavior for the case of a flat plate. And the criterion here, the limiting factor, is approximately the ratio of diameter over length, and length is the vertical length of the cylinder, is 35 times the Grashof number to the power minus 1 over 4. And in that case, we can approximate the problem of natural convection around a vertical cylinder as the natural convection of a vertical plate. If we place the cylinder horizontally, we of course get a totally different situation. Here we will see that the flow is rising around the cylinder, and if the Grashof number is very small, then this will be a laminar flow that nicely follows the contours of the cylinder. If the Grashof number is bigger, then we'll see that we have a turbulent flow developing above the cylinder, and we see that here the low density air rises in a complex flow pattern. For the laminar case, we can find the expression for the Nusselt number based on the diameter as 0.53 times Grashof times Prandtl to the power 1 over 4, where 1 over 4 is the exponent that we have also seen before in for the other laminar cases. For the turbulent range, where we have the larger values of the Rayleigh number, we have 0.13 times Grashof times Prandtl, which is the Rayleigh number to the power 1 over 3. Now, these approximative relations were obtained by Bailey in 1972, and those are the ones that we use here. And here you see the graph of Nusselt versus Rayleigh number. Again, we looked here at horizontal cylinders, isothermal surface under the influence of laminar and turbulent flows. Now we can look at horizontal plates, and this is where it becomes a bit interesting, because here we have two different problems that have the same correlation, and this is because we can look at the problem of a flat plate that is heated with a hot temperature on the top side, and in that case we will have the hot air rising, so we will have different kinds of plumes, flow plumes of the convection rising upwards, and usually there are a few above a plate. And if we now turn the problem around and we have a plate that is cooled on the bottom side, then we'll have the same type of flow patterns, because the cool plate now decreases the density, and the cold air will then move to the bottom. So this is why these two problems are similar. In the laminar range, we have the Nusselt number is 0.54 times Grashof Prandtl to the power 1 over 4, again the 1 over 4 for laminar. In the turbulent range, we have an expression with a constant 0.15 Grashof Prandtl to the power 1 over 3, and that is indeed the larger exponent that we saw before. Now these correlations are based on the measurements on a square plate, and they can also be used for rectangular and circular surfaces, as long as we take into account that one of the side lengths is taken as the characteristic length in the Nusselt number. And usually this is indicated with the correlations that we can use, how to apply them to these general cases. We can then look at the next case, where we have a horizontal plate in a laminar and turbulent flow with an isothermal surface, but then we have a cooled upper side and a heated lower side. And this case is different from the one before, because if we have a heated upper side, the flow can freely move upwards. But if we have a heated lower side, then the flow has to curve around the plate, so the plate itself is blocking the flow. That means that we have less efficient heat transfer. And in the same way here, the cold air is decreasing in density, and it wants to move towards the plate, and it has to move around the plate if it can. So here we have a correlation Nusselt is 0.27 times Grashof Prandtl to the power 1 over 4 for the laminar flow. And this is after Holman, a paper in 1976. And for the here you see the flow pattern. The flow moves to the plate and then is blocked by the plate, so it will move down again and try to move around. And the same you can see here with the cold flow approximating the plate. Finally, we can look at a similar case, a plate heated on the upper side and cooled on the bottom side for the case of a constant heat flow. That is where we have the heat flow given, where you see two correlations. Nusselt is 0.13 Grashof Prandtl to the power 1 over 3. And in the turbulent range, which is valid for Grashof Prandtl to the power between 2 times 10 to the power 8 and 10 to the power 11, there we see 0.16 Grashof times Prandtl to the power 1 over 3. Also, these correlations are taken from the work of Holman. Then the final case is if we turn this problem around and we have the heat flow given and we have the upper surface cold or the lower surface warm, then we have Nusselt is 0.58 Grashof times Prandtl to the power 1 over 5 for the laminar range, and that is the only one that is given here. This brings us already to the end of the lecture with the comprehension questions. First of all, which dimensionless numbers must be taken into account when applying the heat transfer laws? Well, in this case, that is the Nusselt number, and here we have the Grashof number and the Prandtl number, and the product of Grashof times Prandtl is also the Rayleigh number. The driving force in driving potential in natural convection are the density differences as a result of temperature. And what are the different cases for horizontal plates and how do they differ from vertical plates? Well, for horizontal plates, we have a case where we, of course, have the upper surface heated and the lower surface cooled, and those are identical. And those, of course, differ from a vertical plate because in a vertical plate we have a much larger length along which the flow is developing. In fact, the main direction of the flow in a horizontal plate is away from the plate, and the main direction of the flow for a vertical plate is along the plate, and this gives a totally different heat transfer. This brings us to the end of this lecture, and thank you for your attention.